Hello and welcome to this video for the 2022 Level 2 Probability paper for NCAA Level 2 Math. So we're just going to get straight into this paper. So we're going to look at the first question, water everywhere. In New Zealand, the average person uses a mean of 227 liters of water per day. There's a standard deviation of 16 liters. Assume that the water consumption can be modeled by a normal distribution. Find the probability that a randomly chosen New Zealander uses between 227 and 427 liters in a day. So this question is really just like using the calculator to find the answer. But if we want to write down the parameters, we have the mean is equal to 227 liters. The standard deviation is equal to 16 liters. And we want to find the probability that sum x is between 247 and 227. So you just plug into a calculator. So your low will be 227, your high is 247, and your mean is 227, and your SD is 16. And you should get the answer to be 0.3944. And this is an achieved level question there. Okay. So, question 2. If two New Zealanders are randomly chosen, what is the probability that they both use less than 210 liters per day? So we're going to use the same methodology to compute the probability that x is 210. So in terms of a normal, then for a normal, we're looking at sum 210, so it might be somewhere here, and the lower tail here, so that will be p of x less than 210. And if you use your calculator, you should get the answer of 0.1440. So we're going to have to make a couple of assumptions here. So we're going to assume that the events are independent. So assume selection is independent. And when I say selection is independent, I'm just saying that the first randomly drawn New Zealander does not affect the second one. So therefore, if we choose the first New Zealander, for example, it's someone that saves water, that's not going to impact the probability of choosing someone that's going to be saving water or not saving water as the second person. So we're going to assume selection is independent, and which is probably, and it's probably valid because it's a randomly chosen. So valid, random. And probably in a normal survey, you're probably looking at selection without replacement. So once you select someone, you probably don't want to select that same person again, kind of like a survey. So if you're surveying, for example, like at school, like how many of the people go to a tuck shop, for example, you probably don't want to be surveying the same person, let's say 5 times. So you probably will be doing a sampling without replacement. But in this case, we're assuming that the population of New Zealand is so large that removing one person doesn't really affect the overall sample. The overall remaining people in New Zealand. So therefore, you can assume probability remains approximately the same. For NCAA Level 2, you don't really have to worry about that, but just something to keep in mind if you're working with a small sample, not small sample, but rather a small population, then if you're doing a sampling without replacement, then you might have to consider the change in probability once you remove someone from that population. But that we can just quickly move on. I got a little bit off topic there. So P of 2, both that equals to 0.1440 squared, and that is equal to 0.0207. Okay, so question II. If two New Zealanders were both chosen from an area that often experiences water shortages, how would you expect this to change your answer to part I above? So if we're in a place with lots of water shortages, I would expect people to be slightly more aware that there's some possible water shortages in their area, and perhaps this might incite people to have a higher rate of water saving compared to the overall population of New Zealand. So I may expect people to be more aware of possible water shortages in this area. Possible water hence more likely to save water compared to the population of New Zealand. Hence, I would expect this probability to be higher. Alright, that's it for this question. So if you can calculate both parts, you'll get a merit grade. If you can get a correct probability here of 0.1440, that's an achieved. Okay. Suzanne lives with her family of 3 children and her partner. She is conscious of water-saving efforts suggested by the council, and so encourages her family to have shorter showers. Suzanne reads that the average shower time of New Zealanders is 8 minutes, with a standard deviation of 2 minutes. She times the showers taken by her family over the next 2 weeks, and she records the results in the graph below. How does Suzanne's household results compare to the normal distribution model with a mean of 8 minutes and a standard deviation of 2 minutes? You should discuss at least 2 of the center, shape, and spread in your response. So we'll just start off with looking at the center, perhaps. And it's always a good idea for these types of questions to maybe just draw out what you expect the normal distribution to look like, just so you have like a rough guideline of looking at both of them at the same time, and looking at maybe what are the differences between Suzanne's distribution and the normal distribution. So for a normal distribution, apologies for my poor drawing, but for a normal distribution here, you expect the mean to be 8 minutes. And we expect some standard deviation to be 2 minutes. So standard deviation is 2 minutes. And we know that for a normal distribution, the distribution is symmetrical. So everything on the left of the mean and the right of the mean is the same probability. So 0.5 on the left, 0.5 on the right. And in terms of the center, let's look at the center of Suzanne versus the normal. And it looks like the center is approximately around 8. So center, it seems the median, what was the shower time? Shower time of Suzanne's family seems similar to that of of the normal distribution. Normal distribution with mean of 8. However, it's good to note that if you draw a line, rough line here, it looks to be right skewed. So in terms of the shape, you were looking at normal is symmetrical about the mean. But clearly, Suzanne is right skewed. But Suzanne is right skewed. And since it's right skewed, we expect some of the larger values, so some of the really high shower times, such as like the 18 minutes and 20 minutes here, to be inflating the mean. So we expect an inflated mean, so a mean that is greater than 8 for Suzanne's family compared to the normal distribution of 8 minutes. So we expect a mean shower time of Suzanne's family to be greater. We expect it to be greater than 8 minutes of the normal distribution's 8 minutes. And that's because we see the distribution there is right skewed. In terms of the spread, okay, it's very important when we talk about the spread. I like to do a little bit of a little trick here. So we know some facts about the normal distribution is that 68% of the data is within, well, this is approximately, in reality it might be 68.0 or like 1 or something, but it just rounds to 68%. So 8% of the data is within 1 standard deviation of the mean. 95% of the data is within 2 standard deviation of the mean. and we're looking at 99.7% is within three. It's within 3 standard deviations of the mean. So why am I bringing this up? The reason I'm bringing this up is because we can really easily look at the spread of the normal distribution compared to that of Suzanne's family. So if you look at the last threshold here, so 99.7% of the data is within 3 standard deviations of the mean. So that means we're expecting most shower times to be within 8 minus 6 to 8 plus 6. So therefore 2 to 14 minutes. So we're expecting most of the shower times to be within that 2 to 14 minutes. However, and when I say most, I mean extremely most, because 0.3% is a very, very small ratio. So we expect almost nothing really to be above 14 minutes. But if we look at the distribution here, we see there's actually a pretty significant number of days that they're showering for more than 14 minutes. So if we look at here, there's pretty significant amount of days of greater than 14. So we would say that this is probably not really representative of the normal distribution of 8 minutes with standard deviation of 2, but rather Suzanne's family probably has a higher spread of times, suggesting that the standard deviation of Suzanne's household shower times is actually larger than that of 2 minutes for the normal. So for the spread, we'll just I think we get the idea here. So terms of here, we'll just we'll continue our answer in terms of the spread. And for the exam, it's probably good to mention that 99.7% of the data within 3SD, so 99% within 3SD. So expect most to be within 2 to 14 minutes. So expect most. I'm just going to use ST for shower time. So expect most shower times between 2 to 14 minutes. But for Suzanne's family, a pretty significant number is greater than 14. 14 minutes. So we expect the spread is larger for Suzanne's family. So or the standard deviation to be larger. Yeah, so I think this is approximately what our answer should look like. So the center, the median is about where we expect it to be. But for the mean, because the data is right skewed, we expect the mean for Suzanne's shower times to be greater than that of the New Zealand population. And in terms of the spread, we're looking at a higher spread for Suzanne's family because we're looking at a pretty significant number of days greater than 14, which is not really matching that of the normal distribution. So if you mention all of these points, you should be getting an excellence, merit level grade. I apologize, I thought maybe it was an excellence, but no, this is a merit level question with 2 comparisons. So 2 comparisons for a merit, one comparison for an achieved. Question D. After 4 more weeks, Suzanne did another survey and found the shower times in her household approximated by a normal distribution model with a mean of 8 minutes and a standard deviation of 2 minutes. Suzanne considers only 15% of the shower times to be acceptable. So now it's following the distribution of 8 minutes and standard deviation of 2 minutes. So we have not very good drawing. So we have mean of 8 minutes, standard deviation is 2 minutes. Okay, sorry about that. So for this question, we're looking at 15%. So Suzanne considers only 15% of the shower times to be acceptable. So in terms of this, probably looking at the left tail here. So only 15% of the times is acceptable. So when she says acceptable, we're looking at probably like the upper bound of how much time you should be spending in the shower, since the question is more devoted towards saving water. So the less time spent, the better. So the highest amount of time is some value here. We're going to go X, and it's going to be 15% of these shower times, which is falling within that acceptable range. So 15% is in some acceptable range. And for this question, it's really just about using the calculator again. So you're going to be using an inverse to find the inverse. So you're going to give it the area. Area is 0.15, left tail. And this standard deviation 2 minutes with a mean of 8 minutes. And you should get that this X value here is 5.93 minutes. So therefore, showers under this time is acceptable. So and this will be a final answer here, and this is a merit level question with a correct final value of 5.93 minutes. That's a merit. To get a achieved grade here, if you only have a correct answer only, that could be an achieved. Or if you find a Z value of 1.036, so if you're converting it to a standard normal with mean of 1 and standard deviation of 1 and mean of 0, if you get a Z score of negative 1.036, then that's an achieved. Okay. Question E. Businesses use about a quarter of Auckland's water. Auckland Council states that about 85% of businesses use less than 2,000 liters of water per day. If the standard deviation for businesses' water is 450 liters, calculate the mean water usage for business customers, assuming that the normal distribution is an appropriate model. Okay, so for this question, we have our normal distribution. So I'm going to have normal here, and I'm going to have some unknown mean, so some unknown mean, and standard deviation is 450 liters. And some information we do know is that 85% of businesses use less than 2,000 liters of water per day. So we're going to have some bound here, which is going to be equal to 2,000 liters, and we know that this entire area here, this area there, is 0.85. So the first thing we want to be doing in this question here, because what we want to do is we want to be using the Z-score formula, so the Z conversion. However, we do need the Z-score, which is the number of standard deviations away from the mean of 2,000 liters. So we should be converting this to a standard normal. So in this case, we know that P of X is less than 2,000 is equal to that entire left tail area, which is 0.85. And we want to find what is the Z value, some Z value of the standard normal. So the standard normal will be a normal distribution. So this will be a normal distribution of 0, a standard deviation of 1, and we're going to be finding this Z value with the area is equal to 0.85. And for this one, you can just use your calculator for this one. So you can get the Z is equal to 1.036. So that will be the inverse normal, but you'll be using a standard deviation of 1 and and a mean of 0. Okay, and you should get the Z value is 1.036 by your calculator. So inverse with mean of 0, standard deviation of 1, and the left tail equal to an area of 0.85. Okay, so now we can say that 1.036 is equal to some X value, which we know is 2,000, minus the mean, which we don't know, divided by the standard deviation. And now we can just rearrange to find the value of the mean, which is equal to 1,533.62 liters, and that would be a per day. And that will be part I. And looking at part II, the council also stated that a small number of businesses in Auckland, so 1.5%, uses more than 15,000 liters per day. So what issues does this raise for your answer to part I and why? So immediately, the thing I'm thinking about here is 15,000. Well, that's much bigger than this mean of 1,500, well, around 1,500 liters per day. That's almost 10 times bigger. And in terms of what I said before in about, I think it was question was question C. So in question C, I did say that about 99.7% of the data is within 3 standard deviations of the mean. So 99.7% of the data is within 3 standard deviations of the mean. So in this case, we know mean is 1533. Well, 1534 if we round to a whole number. And 450 times 3 is equal to 1350. So we expect 99.7% of the data to be within 1534 minus 1350 to 1354 plus 1350. But 15,000 is much, much bigger than that. And it's actually a pretty significant number, or 1.5% of businesses that are using more than 15,000 liters per day. So we're just going to say that so you could actually calculate how many z-scores away that 15,000 is. So 15,000, it's about if we do it just correctly, so 450, it's about 30 z-scores away. So we're doing, it's about 1,000 is 30 SDs or standard deviations away from the mean, for the normal. We would expect there to be a very small, almost zero. It's a very small, almost zero businesses to be using 15,000 liters per day. 1.5% is much bigger than this. It's much bigger. So the current normal distribution may not be suitable. So the current normal distribution may not be suitable. The current data suggests that the spread might actually be larger. So this suggests the spread may be larger than 450. And that's really all we need to be saying here. So yeah, it's about 30 standard deviations away from the mean. So this was obviously not going to be fitting the correct distribution for the normal. And if you can get both part I and part I explained to a pretty good level, then you'll get an excellence of a grade. Or rather, it's a T2. They're doing T2 for good explanations. And if you'll get a T1, an excellence of 1, if you find the correct mean value with correct working or diagram. For a merit, if you have a good discussion, you'll get a merit. Or if you have an incorrect mean found, but with a good working, you'll get a merit. And if you find the Z value in part EI to be 1.036, you'll get an achieved. And what T1 and T2 means is just like T1, if you get a T1, you'll just get E7 for this question. And if you get a T2, you'll get an E8. So that's really the only difference between T1 and T2. Okay. So question 2. So LAWA conducted a survey and tested some New Zealand rivers in different land types to see if they were safe for swimming. The results from the survey are presented in table 1. Okay, so that's our data. What is the probability that a randomly chosen river from one of the tested is an urban river and is unsafe for swimming? Okay, so for these types of questions, these table ones, you have to be looking at what are we choosing from, and what are we trying to see? What are we choosing? Okay, so we're choosing from all of the rivers of those tested. So all rivers tested, so that means all of them, which is 810, and we're looking at those that are urban river and is unsafe for swimming. So urban river and is unsafe for swimming. So that would be urban and unsafe for swimming. So 57. And that would be equal to, P is equal to 57, 810. And if you want to do it as a decimal, decimal would be 0.0704. And that's an achieved level question there. Question II, is the river and the native vegetation more likely to be safe for swimming compared to that of an exotic forest area? So just going to compare the two probabilities. So for the river and native vegetation, we're selecting from all native vegetations, and for the second one, we're selecting from all exotic forest areas. So for native vegetation, so the probability that it is safe, given that we're selecting from native vegetation, that is equal to 146 over the total, which is 194. So we're looking at this column here. And that is approximately 0.7526. And for the exotic forest areas, we're looking at P of safe, given that it's an exotic forest area, then that will be equal to, we're going to be looking at this column here, and that will be 15 over 26. And that is around 0.569. And we're seeing that our native vegetation is probably more likely to be safe for swimming. So therefore, native vegetation river is more likely to be acceptable or safe for swimming. Than exotic forest area. And that's our answer for this question. This should just be a merit level question. So comparing the two probabilities and giving a conclusion is a merit. If you can get one correct conditional probability, so either this or this, isn't achieved. The actual proportion of New Zealand rivers in each land type is different to those in the survey summarized in Table 1. In fact, 48% of rivers are in native vegetation. We know that 5% are in exotic forest, 46% are in pasture areas, and 1% are in urban areas. Use Table 1 and these proportions to estimate the percentage of all New Zealand rivers that are unsafe for swimming. Okay. So for this question, probably the easiest or the most intuitive way to be doing this is just basically like using, we want to find the probabilities. So one, we're going to find, so we're going to find P unsafe for each river using the table. And then we're going to be weighting them by their prevalence in the population. So this data here, so weight them by the if I can spell, that'll be great. Prevalence in the actual proportion. The actual proportion. Okay. Okay, so we might have a little bit of work to do since I think there's 4 of these to go through. So hopefully I have enough space. So for native vegetation, we're looking at P is unsafe given that it is a native river. So P unsafe given native. That is equal to 48 over 194. P unsafe given that we're looking at an exotic forest area. That is equal to, if we go back to here, so it's unsafe. So unsafe, which is 11 over the total, which is 26. So that's 11 over 26. Look at P, unsafe, given it is the next one, which is pasture, which is 104 over 528. So looking at pasture, unsafe given pasture is equal to 424 over 528. And probability that it's unsafe, given it's an urban, if we go back to our table, the table will show us that unsafe would be 57 over 62. So 57 over 62. And that will be all the probabilities calculated. And now we just need to weight them by the prevalence in the actual population. So in this case, we'll be doing P unsafe that is equal to the sum of the prevalence multiplied by the probability that it's unsafe given that it's that area. And that will just be 48 over 194 times the native, which is 0.48, plus 11 over 26 times the prevalence of EFA, which is exotic, which is 0.05, plus 424 over 528 multiplied by 0.46. And finally, we're going to be adding 57 over 62 times 0.01. And that's equal to final answer of 0.5186. And if you want to write it as a percentage, that will just multiply by 100. So that's 51.86%. Okay, so part III and part 4 is actually linked together. So we'll look at part 4. How confident do you feel that this probability will be correct for all New Zealand rivers? Okay, so we're gonna be when we're asking questions about correct for all New Zealand rivers, the main question we're asking here is this data representative of all of the data in New Zealand? So we're looking at the survey methodology, and we're going to be, in this case, we also have the actual results, so we can do a little bit of comparison with that actual results to see whether or not it's representative. And immediately, the first thing that really caught my eye here was just that there's 194 native vegetations in the survey. However, in the actual New Zealand, native vegetation makes up 48% of all rivers. But clearly, 194 over 810 is clearly much less than 48%, and it's pretty significant amount. Like this is probably around like 25%, which is about half of what you would expect in the real population. So immediately looking at that, that's a massive red flag for this survey, in my opinion. And if you want to look at the other points of the survey methodology, well, it doesn't tell you too much. So conducted a survey, tested some New Zealand rivers and different land types. So one question you might be asking is, was it a random survey, or maybe were some locations, like for example, like maybe some city areas were more likely to be surveyed, or was it completely random? So these are some things that you need to ask, but since they didn't tell you, you don't really want to speculate. So, but just in general, like it's good to ask yourself some questions when you're looking at any type of data. So was it random? How was the survey done? So in this case, it doesn't tell you too much, but it does tell you that it's a from 2020 report that is 2 years ago. So it could be a little bit of, probably not the biggest point. I think the biggest point still stands that this is completely like off from the real number. But we can also mention that maybe 2 years later, that there are some changes to some rivers. Maybe some rivers have been somehow maybe removed, or somehow if it can be removed. I'm not too sure exactly how it works, but if a river can be removed or something, that might have affected the data. So we say that I don't feel confident because of significant discrepancy maybe between the real data and survey. For native rivers, for native vegetation, the actual proportion was 48%, but for the survey, it is around 194 over 810. That's about 25%. Survey is 25%, which is much lower than 48%. Data might not be representative. So data might not be representative of all NZ rivers. Data was sourced 2 years ago, so maybe we can mention that briefly. So data sourced 2 years ago. Could be some changes to some rivers. Could be, for example, some rivers might have been cleaned since then, or maybe some rivers have gotten more dirty due to pollution. So it could be changes to safeness. Not really a word, but you know what I mean? So it changes to safeness of rivers. Okay, and that's approximately what you need to do for this question. It's a little bit wordy, a lot of things to do, but in general, I don't think it was too bad, but there's a lot of work. And this will get you an excellence level grade if you can do both part I and IV. So that'll be an excellence grade there. If you find at least one probability of a river being unsafe, so at least one probability, so one of these four is a merit. And if you can find one probability found, so any one probability is an achieved. Oh no, I think I got that the wrong way around. So sorry, so this isn't achieved, so any four of those isn't achieved. And any one of these is a merit. Okay, that makes more sense, okay. Okay, so question B. Mia and Joe want to go on a holiday near a swimmable river in New Zealand. They find a summary table of popular riversides in the North and South Island that are monitored regularly to check if they are swimmable. What is the probability that a river chosen at random from these monitored sites is safe for swimming? So again, we're looking at the entire sample, so all of the rivers here, and probability that any river is safe, so it's supposed to be P safe. That equals to the total number of safe ones, which is 170, divided by the total number of rivers, which is the total sum of all of the rivers sampled, and that is 278. That is equal to 0.6115, and that's an achieved level question there. Question II. Mia looks at the data and says it is more than twice as likely for a river in the North Island to be unsafe for swimming compared to a South Island river. And Joe says it's only 20% more likely for a North Island river to be unsafe for swimming compared to a South Island river. Explain each person's reasoning and decide if either reasoning is supported mathematically. So we're going to use some relevant calculations to support the answer. So this is just screaming out to be a relative risk calculation here. So we're going to be calculating the probability that a river is unsafe given it's in the North Island, and comparing this to the probability that a river is unsafe given that it's a South Island river. So we're going to look at the probability that it is a unsafe given that it's a North Island river. And that will be equal to 74, so unsafe over the total, which is 179. And we're going to look at P unsafe, given that it's a South Island. And that's equal to the total unsafe, which is 34, over the total number of rivers, which is 99. I think it's 99. Yeah, it's 99. And then we're going to compare the two risks by dividing them to find the relative risk. So our relative risk is equal to 74 over 179 divided by 34 over 99, and that is equal to about 1.204. So therefore, we can conclude that it is about 20% more likely. It's about 20% more likely for North Island rivers to be safe for swimming, to be unsafe for swimming rather, to be unsafe. We're looking at unsafe rivers, so unsafe for swimming compared to the South Island. Hence, Joe's reasoning is correct. So Joe's reasoning is correct. And okay, so in terms of Mia's reasoning, I think the problem with that reasoning is probably she is looking at 74 and 34. So in this case, 74 over 34. I mean, that's approximately 2 point something. So that's about 2. But that's not correct, since you can't just do 74 over 34 because you don't know the total sample sizes of the number of North Island rivers in the sample and South Island rivers in the sample. So if they're both the same, then in fact this is actually fine. But the fact that they're not the same, then you cannot do this. So therefore, Mia's which disregards the sample sizes, basically. Okay, and that's it for this question. So if you can get the correct relative risk, explain the interpretations, so 20% more likely for North Island rivers to be unsafe compared to the South Island, and you're saying that Joe's reasoning is correct, and you're looking at Mia's reasoning of 74/34 is not really correct because it's a different sample size. So if you cover all three of those points, you'll get a T2. To get a T1, if you can interpret the relative risk in context and explain why Joe is correct, then you'll get a T1. So you have to explain why Joe is correct and why Mia is incorrect to get the full mark for this question. Alright, so question 3, lucky last. So a large online survey was carried out asking 2,500 New Zealanders for their views about water use. 87% were concerned about water shortages, and 80% usually try to save water. 18% only try to save water when the restrictions are in place. 2% never try to save water. Of those not concerned about water shortages, about half of those usually try to save water, a quarter of those try to save water when restrictions are in place, and the rest never try to save water. So use this information to complete the probability tree below. So this should be pretty straightforward since we have all the data. So 87% were concerned about water shortages, so we know 0.87 is concerned, and we know that 0.13 are not concerned. And of those that are not concerned, we know that they usually save water, only save... Okay, I'm not going to write the whole thing out, so only save when restrictions, never save. Okay, so we know that of those that are not concerned, we know that none of them never save water. And we know that a quarter of them try to save when there's restrictions, so that's 0.25, and half of those, the rest never, sorry, it's not 0, I misread that, so this is 0.5, and then the rest as in 0.25, so the rest of them will try to save, will never try to save water, sorry, I misread that question, so 0.50, 0.25, 0.25. What is the probability that a respondent chosen at random is concerned about water shortages and usually saves water? So we know that P of concerned and saves water is equal to 0.87 times 0.8. And that should be equal to 0.696. And that's an achieved level question. Of 2,500 survey respondents, how many said they only save water when restrictions are in place? Okay, so we're going to look at P of only save water with restrictions. So with restrictions is equal to the probability that they're concerned and they save with restrictions added to the probability of they're not concerned and restrictions. So this is equal to 0.87 multiplied by 0.18 plus 0.13 times 0.25. And that is equal to 0.1891. And we want to find the expected number. So the expected number is equal to the total number multiplied by this probability, which is 0.1891. And that is about 472.75. And we can just round this one to 473 respondents. And that's the answer for this question, so 473, which is a merit level question if you can get the correct number of respondents and the whole number. And achieved will be a correct probability. So here will be achieved. Question B. A secondary school teacher wondered if young people's views would be similar to those seen in the online surveys described in Part A. She surveyed 200 students from years 9 to 13 at 2 local high schools. She found that 70% of students were concerned about climate change. And of those concerned about climate change, 85% were also concerned about water shortages. 55% of those who were not concerned about climate change were concerned about water shortages. So we can draw a probability tree, and we can just draw out the probability tree. So first thing is whether or not the student is concerned. So we have concerned, not concerned. Maybe a bit bigger than this. That's a bit small. We have a lot of space, so might as well use it. So we have concerned and not concerned. And of those that are concerned, those are worried about climate change, and those are not worried about climate change. Same thing for the here. So we have those that are worried about climate change and those that are not worried. So we know that 70% of students are concerned about. Oh, sorry. Okay. So climate change is on the first one. So this is climate change. And this is the second one is water shortages. Water shortages here. Okay. So concerned about water shortages, not concerned. Sorry. Okay. Concerned about water, not concerned with water. Concerned with water, not concerned with water. Okay. So 70% were worried about climate change. So therefore, 0.3 are not worried about climate change. Of those who are concerned about climate change, 85% were concerned about water shortages. So 85 here, 15 here. 55% who are not concerned about climate change were concerned about water shortages. So 0.55 and 0.45. So draw a probability tree and use it to find the probability that a student chosen at random is concerned about water shortages. So probability concerned water is equal to P of concerned climate change and concerned water plus P of not concerned of climate change and concerned water. So this is equal to 0.7 times 0.85 plus of 0.3 times 0.55. And this is equal to 0.76. And this is an achieved level question here. Okay. The teacher also found that the probability that a student saved water was 2 times greater than if they were concerned about water shortages than if they were not concerned. The probability that a student saved water was the same as whether they were concerned about climate change or not. The overall probability that a student in the survey saved water is 0.5632. Find the probability that a student is not concerned about climate change and not concerned about water shortages and does not try to save water. Okay, so probability that a student saved water was... Okay, so probably we should refer back to our tree here. So we have concerned about climate change, not concerned. We have concerned about... So probability. So we have concerned with water, not concerned with water, concerned with water, not concerned with water. So probability that a student saved water was 2 times greater than if they were concerned about water changes than if they were not concerned. So we can branch this one out to save water, not save water, save water, not save water, save water, not save water. So the probability that a student saved water was 2 times greater than if they were concerned than if they were not concerned. So if we have probability of students saving water is 2 times greater. Okay. Probability of students saving water is the same. Okay. So probability that a student saved water was the same, whether or not they were concerned with climate change or not. So in this case, the climate change actually doesn't really matter in this case. Okay, so we can simplify this a little bit. I misread. Simplify the question a little bit here. So realistically, all we just have is concerned with water, not concerned with water. And we have save water, does not save water, save water, does not save water. Not save. So if they were concerned about water, so their probability was 2 times greater to save. So if this was x, then this is 2 times of x. The probability that a student saved water was the same, whether or not they were concerned about climate change or not. And the overall probability that a student in the survey saved water was 0.5632. So therefore, P, I'll probably use black. P of 0. What am I doing? Sorry. P of save water. Okay, And in the previous question, we would have calculated randomly chosen student was concerned about water shortages is 0.76. So 0.5632, that is equal to 0.76. Okay, and we have 0.5632 is equal to 0.76, 1.5. That is equal to 1.76x. So we need to divide both sides by 1.76x to get x. So x equals to 0.32. And we want to find the probability that a student is not concerned about climate change, not concerned about water shortages, and does not try to save water. Okay, so in this case, we need to do not concerned about climate change is 0.3. So probability not concerned, CC, so not CC, not water shortages, no save water. That is equal to 0.3. That is the probability that it is a not concerned about climate change, multiplied by not concerned of water, which is 0.45. And then we need to multiply by the value of not concerned of water, and we have 1 minus x here, 1 minus x there, and 1 minus x is 0.68, so 1 minus 0.32, so this is 0.3 times 0.45 times 0.68, and that is equal to 0.0918. Yeah, it's a little bit confusing question there, but just after reading that, the probability that students save water was the same, whether or not they cared about climate change or not. That simplified the tree diagram, so we were able to find the answer there. So that's 0.0918. And that's a T2 for correct probability. So get a T2 if you can get that probability. Question III. So the teacher uses the findings of both surveys from Part A and Part B to claim that New Zealand's secondary schools are about 25% less likely to save water in their homes than the general population. So we know that the probability that it was just stated in the previous question that we P save population secondary school, that is equal to 0.5632. And the probability that we're saving in the general survey, so save general, we do need to calculate this one, but we can use our tree diagram on Part A to do this. So we can do P save is equal to 0.87 times 0.8 plus 0.13 times 0.5. And that should give us an answer of 0.761. So we know that P save general is 0.761. And the relative risk is equal to 0.5632 over 0.761. That equals to 0.74. So probability of students saving water is about 0.74 or 26% less as likely as someone saving water in the general population. So claim of 25 relatively close. So claim of 25% is pretty close. Hence, claim valid. Alright, so that's the first part done. So discuss the validity of the claim, and in terms of the validity of the claim, okay, so the claim of 25% is I mean, in this context of the pure calculation, it is valid. But perhaps we might also want to consider consider the survey methodologies. So there might be I think so in terms here, claim is valid in terms of however overall validity may be questioned. However overall. For example, if you refer back to our survey methodology, so survey methodology, we're looking at 2 local high schools, and it's 2 local high schools might not be representative of all students in New Zealand. Unlikely to be representative, as it could be some area dependent factors that could affect their water usage. So that's a big issue. It's a pretty big issue on the survey methodology. And also it was an online survey. So in terms of online surveys, some people might be less likely to want to do online surveys, and there's also an opt-in bias. So some people who choose to do the survey and the people who don't choose the survey, there could be statistical differences between their water usage as a confounding factor. So that's also something we need to consider. So 3 questions. So 2 local high schools may not be representative. So 2 local high schools of all students in New Zealand. Online survey could be biased. Some people more or less likely to do the surveys. So this is like a confounding factor. And there's no, and this, I mean, the categorization of whether or not you're saving water is a bit unclear. So a bit unclear on what exactly it means to save water, since there's also another category that says that some people save water when there's restrictions in place. So does this actually count in whether or not the person saves water? So that's actually a valid, unclear definition, a bit unclear definition of what is saving water. So i.e., does saving water during emergency count? And that's about where this question is at. So you're having a good discussion of the calculation, and the good calculation and good discussion of the validity is an excellence. And if you can get correct probabilities to correct a relative, correct probability of water in the general population, and the validity of the claim discussed, then you'll get a merit. If you find 0.71 with no discussion, that's an achieved. Or if you have an alternate interpretation, you might have an achieved there as well. Alright, so thank you for watching this video, and I hope you enjoyed, and I hope to see you all in the next one.